Welcome to Work, Energy, and Power. I want to preface this video by saying that this is a really big topic in physics, which means that I'm not going to be able to cover absolutely everything you need to know about it in one video. I'm going to try to touch on the most important concepts, specifically with a focus on mechanics, so when you see these concepts again, when you talk about electricity, I'm not going to cover all of that in this video, but I want to try to cover as much as I can to give you a good grasp on these concepts. So, let's start with what is work. Work is force times distance. So this is going to be in units of Newton times meter or joule. The other important concept in work is that work is going to be equal to the change in kinetic energy. And we'll learn what that is in just a second. But as we learn about different types of energy, one important thing to know is called the first law of thermodynamics. And the first law of thermodynamics is otherwise known as conservation of energy, and it says that energy cannot be created or destroyed. So energy can be transformed into other forms, but it cannot be just poofed in and out of existence. When we look at work as force times distance, one important thing to recognize is that when we multiply these together, the force and distance have to be going in the same direction in order for this quantity to exist and be positive. So if you look at the first row in this figure, you can see that the force and the distance are kind of going in the same direction. Here what we have is we have a vector, or like a quantity that has a direction, that is going at an angle, right? And when we have a vector going at an angle, what we need to do is take components of it. So we can have the horizontal component of this force and the vertical component of this force, right? And those are going to add into our vector sum. So out of these two components, I'm going to call this FH for horizontal force, and this is FV for vertical force. Only the horizontal component is doing work, and that is because the distance is going in the horizontal direction. The vertical component of this force is doing no work. So if I wanted to calculate the work in this situation, I would have to know this angle, I'm going to call it theta, and we would have to multiply F times, would it be cosine or sine? In this case, it would be cosine. So F times cosine theta, because cosine is the adjacent over the hypotenuse, right? SOHCAHTOA. And then we would multiply this by the distance, which my book shows as S. I don't think that makes a lot of sense. Usually I denote distance as a lowercase d. Some books will show you a formula that says work is force times distance times the cosine of the angle. I don't like to do that because it's not always going to be the cosine. Because let's say that instead I gave you this angle, which I'll call alpha. If I gave you that, then this would be the vertical component, would be the cosine component, and the sine component would be the horizontal. So I don't like to just memorize a formula that has cosine theta in it, because I want to be able to say sine if I have to say sine instead. So when you get an angle, just look at the components and look at SOHCAHTOA and see which one does it make logical sense to use. But in this case, because the component we're looking at and the distance are going in the same direction, the work exists and is positive. If you look at the second row of this figure, the force and the distance are actually going in opposite directions. Now, how can that be? If you push something, shouldn't it go in the direction that you're pushing it? Well, sometimes we have more than one force, and one force will beat out another. For example, friction and air resistance do negative work because they are going in the opposite direction of the direction that something is moving. If you look at the last row here, what's happening is that we have a force that is going perpendicular to the distance that the thing is going. So again, this could be the result of many forces acting on the same object, and this one force just happens to be going perpendicular, and something else is pulling it in that direction of the distance, right? So in this case, there is no work being done because there is no component of this force that is going in the direction of the distance. So here are some more examples of positive or negative or non-existent work. For example, in this upper figure, the guy is holding the weight, but he's not lifting the weight. His arms are exerting an upward force on it, but there is an equal downward force of gravity. So the total work being done is 0 because there's no distance that's happening to this weight. In the lower example, the barbell is being lowered to the ground. So what's happening here is that this person, the weightlifter's hands are still pushing up, and gravity is pushing down. So gravity is doing positive work, and the weightlifter is doing negative work. So now we can look at the different forms of energy. So we're coming back to this concept of conservation of energy, which remember is the first law of thermodynamics that says energy cannot be created or destroyed. Often, one type of energy is going to decrease and another type of energy will increase as a result, because we can't just take that energy away. So we've got kinetic energy, which is the energy of movement, and this one has a formula of 1/2 times mass times velocity squared. And then we have potential energy, and potential energy is energy that is stored that can later be used. And we can do this in many different ways. We have gravitational potential energy, so you can think of this like if you were to stand on a chair, you could fall, and then movement or kinetic energy would result. Gravitational potential energy has a formula of mass times gravitational acceleration, which is usually like 9.8. Some people will round it to 10, depends on the class, times the height. We have elastic potential energy, and I'm going to come back to that one in a few slides. We have electric potential energy, and that one I'm going to have to make a whole nother video on because there's a whole set of formulas that come with that. And then we have chemical potential energy, and chemical potential energy does not often appear in physics. It appears more in chemistry and in biology. So for example, if you've watched my cell respiration videos, we are taking glucose and using its chemical energy to convert to the chemical energy of ATP and also some thermal energy, which is like the heat that you give off when you expend energy. And then we have thermal energy, which, like I just said, is heat. Thermal energy can't really be used to do work. Once we make energy into heat, it just kind of dissipates into the surroundings, and it's difficult to harness that again. So let's look at an example of conservation of energy. In this problem, a 4.8 kilogram watermelon is dropped from rest from the roof of an 18-meter tall building and feels no appreciable air resistance. So we're going to calculate the work done by gravity on the watermelon during its displacement from the roof to the ground, and then we're going to answer, just before it strikes the ground, what are the watermelon's kinetic energy and speed? So how can we start this problem? We've been given a lot of information, but the first thing that we're asked to figure out is the work done by gravity. So the force due to gravity times the distance that this thing has gone in the direction that gravity is pulling it, that will get us the work done by gravity. So we have the formula we're using of work equals force times distance. So that force can further be broken down into mass times acceleration, which in this case is gravitational acceleration. So here we have a 4.8 kilogram object, right? And we're going to multiply it by 9.8 meters per second squared. And that will be multiplied by the distance of 18 meters. This gets us a work of 850 joules. So that is the work done by gravity on this watermelon as it falls. So now we are asked, just before it strikes the ground, what are the kinetic energy and the speed? So remember that work is the change in kinetic energy. This watermelon is dropped from rest. So it started with no kinetic energy, and now it's going to have some kinetic energy that we don't know, but that has to be equal to the work done on the watermelon. The only force that has been acting on the watermelon was gravity. So the work done on it is the work done by gravity, is 850 joules. So the kinetic energy is also going to be 850 joules, because work is the change in kinetic energy. So now we can use this to get the speed, because we know that kinetic energy is equal to 1/2 times the mass times velocity squared. So we have everything except for velocity, and we're going to be doing algebra to get velocity. It entirely depends on your preference whether you like to do the algebra with numbers or with variables. I'm going to do it here after putting in the numbers. So we have 850 equals 1/2 times 4.8 times v squared. And we are solving for v. So first we can multiply by 2. So that's going to get us 1,700. Next we can divide by 4.8, and this will get us 354. Finally, we can take the square root of both sides, and that will get us v is equal to about 19 meters per second. So there's our answer. And actually, we usually don't even need mass to get speed in these types of problems. If we had had only part B, number 2, for the speed, and we hadn't been asked for work, we hadn't been asked for kinetic energy, we could have done this using potential energy, mgh, equals kinetic energy, 1/2 mv squared. And we can cross out mass. And then we could solve for velocity. Next, I want to go back to elastic potential energy, and this has to do with something called Hooke's law. Hooke's law has 2 equations that tell us how springs work. The first one tells us about force, and it says F equals kx. So what is kx? Well, k is the spring constant, and it depends on what kind of a spring you have. They either have to give it to you in the problem, or they have to have you solve for it. X is the displacement of the spring. It can be compressed or it can be stretched, but the distance of x is the distance from equilibrium that you have taken the spring. The second equation tells us about potential energy. Now, I didn't introduce this with our gravitational potential energy, but the variable that you might often see for potential energy is U. So U is going to stand for potential energy, and that can be any type of potential energy. So for a spring, this is equal to 1/2 kx squared, where k again is the spring constant and x again is the displacement from equilibrium, either by stretching or compressing the spring. So if I'm compressing a spring and I want to know what the change in velocity is, I can use potential energy and kinetic energy to figure that out. So let's look at an example. Here we have a woman weighing 600 newtons steps on a bathroom scale that contains a stiff spring. In equilibrium, the spring is compressed 1 centimeter under her weight. Find the force constant of the spring and the total work done on it during the compression. Okay, I did not include the figure, but basically there's a spring inside the scale and she steps on the scale and the spring gets compressed. And we want to figure out what is going on with energy in this problem. So to find the spring constant, or the force constant, same thing, that's K, we have 2 options. We can use either F equals Kx, or we can use U equals 1/2 Kx squared. Now pause the video if you need, but I want you to think about which equation are we going to use and why. Alright, are we back? So did you figure out it was the first equation? If so, great job. We do not have potential energy, but we do have F and we do have X, which allows us to solve for K. So we can take this equation and we can write that 600 newtons equals K times, and we're not going to use 1 centimeter. We are going to have to use meters. So this is going to be 0.01 meters. And I should do a significant figure. It's 0.010. So there's our equation, and now all we have to do is solve for K. So if we do 600 and divide this by our X, and this was in newtons, I didn't write that unit, equals K, this is going to be 6 times 10 to the 4th power. And the units are going to be newtons per meter. What about the work done during the compression? We actually have 2 ways to solve for this. So we can solve for this using work equals force times distance, or we can use the change in potential energy. So if we use force times distance, we have work equals force times distance equals 600 newtons times 0.01 meters. And this is going to get us a value of 6 joules. Now if we do it our other way, we can use U equals 1/2 kx squared. We can arrive at the same answer by using the change in potential energy, U equals 1/2 kx squared. So if we do this, we just plug in. For k, we have 6 times 10 to the 4th power, and then for x, we have 0.01 meters. And we square that, and we would get the same thing as we got from our force times distance work. So now I want to talk about a concept called power. Power is work per time. So the formula looks like this. And we can also equate it to force times velocity. Because if we do work per time, work is joules or Newton times meter, right? And here is seconds for time. Force is newtons, and velocity is meters per second. So this is exactly the same thing. Power is expressed in a unit called a watt, which is a capital W, and this is equal to joule per second, or Newton times meter per second. So let's look at a problem with power. In this problem, a 50-kilogram marathon runner runs up the stairs to the top of Chicago's 443-meter-tall Willis Tower, the second tallest building in the United States. To lift herself to the top in 15 minutes, what must be her average power output? And we're not going to do the end of the problem with expressing it in horsepower because I don't know that conversion off the top of my head. If you needed to do that, you would be given a conversion factor. So to do this problem, we can use work in terms of potential energy. So we're doing gravitational potential energy here because our kinetic energy, which is her running up the tower, is going to get transformed into gravitational potential energy when she's up at the top of the tower. So for gravitational potential energy, we have mgh. So here that's equal to 50 kilograms times 9.8 meters per second squared times 443 meters. This gets us a value of 217,070 joules. But we're not done yet. So we have to take this and use power equals work over time. So if we take minutes, 15 minutes, and convert to seconds, we have to multiply 15 by 60 because we have 15 minutes times 60 seconds per 1 minute. And that's going to get us 900 seconds. So if we take this number and divide it by that number, we get about 241 watts. And that's our power.